Cool. Yeah, thanks everyone, and welcome to our talk. We will talk a bit about recent stuff we've done in JavaScript engine fuzzing land. So we, that's Carl and myself. These days we work on the security of V8, which is the JavaScript engine powering Chrome. And as you can maybe imagine, that comes with all sorts of fascinating technical challenges, some of which you will see today. I think our talk, we could have also named it something like finding cool bugs with little compute, because basically we will tell you how you can also find interesting bugs in JavaScript engines with like, one beefy machine and like over the course of a weekend or so with our fuzzer. So, right, so our fuzzer, that's Fuzzing. It's open source. You can find all the everything we will tell you today, all the code is open source. And actually this fuzzer was released here on the stage 4 years ago. And pretty much today we will tell you what has happened since then. Kind of to start with, I want to do a brief recap of what Fuzzing is and how it works. The core idea here is that it works on its own intermediate language, which we call FuzzIL. Here you see an example. It's probably relatively self-explanatory, like you have this creates a function that then calls a method slice on an array and so on. The key point here is that this intermediate language is designed to be easy to mutate. This is the key design choice here. We want this to facilitate meaningful code mutations. Here you see some example of really simple but meaningful mutations. So for example, we turned the constant 1 into 100. We added some random code, the set property here. We changed some inputs around, right? Like what used to be V3 is now V1. And all of these are interesting mutations, and they are really easy to implement in this model. One of the more advanced mutations we can do is called splicing. Here you see an example. We have the program on the left that's has maybe a function. And then from the program on the right, we want to take some of the code and move it over into this other program. And here in this case, maybe we decide we would like to take the return operation. And we can do this because we are splicing into a function, right? We couldn't take a return and put it somewhere else. It has to be in a function. And so if we decide to take the return, we want to also take some of the inputs. And so you end up like with this green, all of this green code, and we can just copy it over, rename the variables, and we have kind of combined these two programs. Yeah. So now, of course, the JavaScript engine doesn't understand our IL. So what we have to do as the final step is we have to convert our IL to JavaScript in a step called lifting. And here you see how this toy program might be lifted to JavaScript. Now again, as I said, this is how Fuzzing basically worked from day one. This finds bugs, this has found a couple dozen interesting bugs back then that had been in these engines for a long time, but it doesn't find enough bugs, let's put it this way. Because, as you may have noticed, there have been JavaScript engine bugs in the last few years still. And so we want to talk about why it's not finding these and what we can do to find these other types of issues. What I want to do now is to kind of explain how we think about this problem in very simplified terms. There's going to be lots of these boxes here, all these circles. Let's imagine this blue area represents kind of the space of all possible JavaScript programs that you can have. And you can imagine this space is gigantic. It's huge, right? And so what a fuzzer would do is it would sample random programs from the space and see if they crash, right? Now, of course, the space is so gigantic that you need some guidance for your fuzzer to guide it towards where you think the bugs are. And what Fuzzing is doing, and what most modern fuzzers do, is they use code coverage as this metric. And so with code coverage, basically it means your corpus, the set of programs you mutate, they maybe come from this area. Probably in reality it's much smaller. The set of programs that increase code coverage in the engine, right? And so then in that case, what your fuzzer will generate is like samples kind of from this green area, right? So like in the yellow, but also around the yellow area, right? Because what the fuzzer does is it takes the program from the corpus and then does a couple of mutation steps and then tries the next one, right? And so you will be kind of in one, you know, obviously it's like a multi-dimensional space, but like you will be in some certain area here. And now the question, of course, is where are the bugs, right? So definitely some of them will be in this green area, probably even quite a few, right? Because like bugs typically are around complex code, and complex code is exactly where code coverage drives the fuzzer towards. But there will also be bugs outside, and that we will just not be finding, or where just the probability is just so extremely low that it doesn't happen in practice. So yeah, so this is the question, how do we find these other issues? There are a couple of things you can do. You know, like one of the easier ideas here is, well, let's not start from scratch, but let's import existing JavaScript code. You know, maybe there are lots of regression tests in that come with these JavaScript engines. So test cases for previous bugs, and you know, maybe there are still bugs like kind of similar to older bugs, like variants, for example, and then maybe you could find them if you start with existing test cases. I mean, this is how like most other fuzzers work, right? Like you give them some initial corpus and they mutate it. Actually, in the case of Fusilli, it's a bit more complicated, because if you want to do this, you kind of need to build a small compiler first. You need to build a compiler that compiles JavaScript to our IL. And so that's why this took like 4 years for us to support it. But it is now possible, you can now do it. So we will also not talk much more about it. Another idea is you could try to use a different feedback mechanism, something other than code coverage, to then hopefully, you know, guide the fuzzer to these other bugs, like expand the yellow area in a sense. This is probably a future research topic. We have vague ideas here, but nothing to share yet. But I think this would be really an interesting topic. So instead, what we want to talk about today, or one of the things we want to talk about, is using specialized fuzzers, mutators. Here the idea is kind of to expand the green area, like make mutations that will get you to certain types of bugs. So to motivate this, let's look at one kind of classic bug from JavaScript engines and see why maybe a fuzzer would struggle to find this. This is a bug quite old, like 2016, but it's a good example of a typical bug class in these engines. What happens here is you have in the like last code line, you're calling a method slice on an array, so you're taking, you know, a part of an array and turning that into a new one. And typically you would call this method with 2 integer bounds, right, like lower and upper bound. In this case, the upper bound is an object. And so in this case, the JavaScript specification says, you know, engine, you now have to fetch, look for a method called value_of, call that, and whatever that returns is your integer value. And now the engine does that, but this value_of callback, it's kind of evil, and it resizes the array. And now the problem here is that we are in the middle of this slice operation. The engine has already done all of the bounds checking and so on. And so the engine doesn't realize that the array has just shrunk from 100 elements to 0, and then it goes out of bounds. And you know, you see like the result array has random data in it, and that's just random memory content. So now why is this hard for like a generic fuzzer like Fusilli to find without help? So what we think is like what I've highlighted in red here is, you know, it kind of needs 3 different things to happen for this bug to trigger. You need to call slice, you need to have an object with value_of, and that needs to shrink an array. And now the thing is here that the fuzzer will get rewarded for doing each of these steps individually at some point, but there's no more reward for combining them in any way, right? Like you will have 3 different samples in your corpus, like one resizes an array, one does value_of, and one calls slice, but there's no reward in whatsoever for combining them. And so a fuzzer struggles with even a fairly simple test case like this one. So let's build something generic that can find these issues. And This is the first mutator we have. We call it probing mutator. What it wants to do is answer the question of, maybe you have a value in your program that's being used in some way. It wants to answer the question, how is this value being used by the engine? Maybe because you're calling a built-in function. So what we do then, the fuzzer instruments this program, puts in what we call probe operations, and then runs this like intermediate program. And at runtime, this probing does some like JavaScript magic stuff where it turns v1 into what's called a proxy object. This proxy object can record all of the operations performed on it, like it will see what properties were accessed and so on. And then it sends all of that back to Fuzzing, right? So in this case, maybe it sees that value of was called or was fetched from v1. It tells that to Fuzzing, and then Fuzzing goes and it's like, okay, I see value of was accessed, and I know value of is typically supposed to be a function, so let me install this, right? And so with this one mutation step, we are already basically 2/3 the way to the bug. And this is quite generic. So here's an example for a bug that this found. It's a very similar bug to what we've seen. Kind of what happened last year is that they added, they made a different type of array resizable. So it was kind of clear that this type of bug would probably reappear, and so it did, right? And so here's an example. You see it's very similar. There's a function that resizes something, and then there's a type conversion happening, and then it does an out-of-bounds access, which in this case is harmless because the feature was designed to not break so easily, but that's a different story. Maybe also interesting, this probing mutator can also figure out how to call APIs, like the top right, the max byte length parameter that you have to give to this kind of array. If Fuzzing didn't know about this parameter, this mutator would also find it, right? It's exactly the same logic. It figures out on this object, max byte length is fetched, so let's install it. We have a second one of these, what we call runtime assisted mutators. This one is called exploration. It wants to answer a slightly different question, which is given a variable that we don't know what it is, what can we do with that? So maybe in this case you have function parameters. This function is being called by internal code. You don't know what v3 is, but you want to use it. And so what Fuzzing can do is it can put in these explore, like what we call explore operations, runs this intermediate program. The explore operation at runtime does all kinds of type inspection stuff, like it uses the type of operator to figure out, is it a number, is it an object, is it a function, whatever. It can figure out all the properties existing on it, and then again, it picks a random thing to do and tells that to Fuzzing. So in this case, maybe it sees there is a method foobar on this object, it decides to call it, it tells it to Fuzzing, and then Fuzzing replaces this kind of abstract explore with the concrete operation that was done at runtime. Now this step is really important, like we cannot keep the explore operation in there, we have to turn it into a concrete operation. Here's one example why that is the case. This is a nice, really nice bug that this found fairly quickly. This was a bug in the optimizing JIT compiler in V8, where basically it tried to inline this array.add method, but then kind of screwed up the type check. So like it wanted to make sure that this object is an array, but you could make another object look kind of like an array, and then it passed the type check, and it got into a type confusion. We know this was found by the explore operation in this case, because Fuzzing at that point didn't know about the add method of arrays. Like the only way it could have found this method was through this mutator, so that's why we know it. But yeah, this is a really cool bug. We did write an exploit for this. Maybe some of you did as well. If you did, I would be curious how you exploited it. But yeah, it is a cool bug. So maybe in terms of our pictures, like this is what we've done, right? We have made these mutators so they like move towards certain types of bugs and let us find these. And now Carl will tell you a bit about what we're still not finding and what we can do about that.
Thank you, Samuel. So we will also have bugs that are somewhat far removed from what the fuzzer will generate with just plain code coverage feedback, right? And in this case, we need to help Fuzzing somewhat more. And yeah, now I want to talk about what we can actually do about this. So for that, we will need to take a step back and actually look at the complexity of a trigger that Fusilli can actually find in reasonable time. And this is the same bug that Samuel just mentioned, right? But now we can actually like try to do some analysis on it and like understand how many steps Fusilli would need to perform in order to create this trigger from scratch. And first, we need to get like an object into a specific state. Then it needs to actually JIT optimize, or like, yeah, JIT this function and that takes these kinds of objects. And then it needs to perform some specific actions with them. All of this takes roughly 9 steps in Fusilli. And you have to be like aware that Fusilli has literally hundreds of choices at each of these steps. So it just becomes increasingly unlikely that Fusilli will find this exact control flow to trigger this bug and this data flow. So obviously there's also some like really hand-wavy counting of these steps, but this is just to get a rough idea of like how complex it is to create these triggers. And now we're also going to take a closer look at this in the wild bug that Google Tag found, and we can do a similar analysis. It is not super important what this trigger does in detail. We are also like planning on releasing an RCA document in the near future. The key part is that it gets an object and the engine into a specific state, and then further performs some extra steps on the object that cause the optimizing compiler to miscompile the setInnerProperty function at the top. So if we do the same kind of analysis here, we can see that it takes a couple of more steps to actually create this trigger. And we can already see 14 is like it takes four more steps from the, like 5 more steps from the other trigger, right? So how can we actually guide Fusilli towards these more complex triggers and make Fusilli find these triggers? Well, if we take a closer look at this sample, right, we can see that some of the steps like get the engine and the object into a specific state. And to reach the state, it usually takes a couple of steps, right? So maybe we can help Fusilli with that, right? And again, Fusilli will get rewarded for finding these steps on its own, right? But not maybe in this specific control flow. So maybe as a researcher, we can say, okay, cool, let's build like a, like a built-in function that we can add to the engine that, like basically like collapses all of these steps into one step so that Fusilli can like just find this more quickly and easily. And this would remove 4 steps from the whole process, right? So this would be more likely for Fusilli to emit. But this obviously takes some specialized research and knowledge. And the idea here is to basically put the human into the fuzzing loop and use basically human-assisted fuzzing, right? Yeah, another thing we thought of is like, okay, maybe as a researcher you have a rough idea of what the code shape of a trigger would look like. In this case, we would have like, 2 functions. And if we assume as a researcher that there is sufficient complexity in the optimizing compiler, and we get an object into this interesting state, and then we also like call the function a bunch of times, then maybe we can find something. Maybe we have this like rough idea of this code shape, right? So in Fusilli, we call these things program templates. And they can be used to roughly describe this kind of code shape, right? We say, oh, we want this like random function with some random number of parameters, and then we want to like basically have some random instructions in there. And then we want to call this like function that gets this object into an interesting state, and then we want to also call this function a bunch of times so that it gets optimized. The cool thing about this build function is that it can basically make use of all of Fusilli's mutators and generators, and it can also splice different programs from the corpus into the specific, into the function, right? And the build function also is able to like basically understand what the fuzzer has like emitted previously, so it can make full use of everything that the fuzzer has already emitted, or the stuff that we have defined, right? And this is the basic logic behind the hybrid engine. Fusilli uses the template, it generates a program, fills in these like build lines with generators and like splicing. Then we also mutate the program a couple of times, and we execute them in between pretty much, right? And see if we can find new code coverage, but also exercise this sort of code shape. And this is like super cool, because we can now actually build like fuzzers for specific parts of V8. In this case, we wanted to fuzz the regular expression engine. We had an internal fuzzer that we wanted to convert into this Fusilli template. We did that, and this is like a simplified version of the template, but it is fairly close to what we actually used. And here we are telling Fusilli to build a function that creates a regular expression and creates a random string, right, and then calls exec on that. And then we also use the build function to do some more stuff, right? And we call the function a couple of times, and then we do some more stuff at the bottom. And the full version of this template has found 2 bugs that have been there for a fairly long time. This is one of them. So the question now is like, well, okay, we actually just like converted one of our internal fuzzers into this template, right? Why didn't the internal fuzzer actually find this, right? The cool thing is that this build function is actually really nice because it allows us to explore the state that we've created with this shape even more, right? And that is just very cool. It allows us to build like these very highly specialized fuzzers, but also like these very like rough shapes of maybe ideas that we have for where we can trigger complexity. And it is also super easy to write these things. Like it only took a couple of hours to basically write this template and get it up and running. And this is an example of also one of these like mini fuzzers where we wanted to fuzz the serializer API. This is exposed in web browsers, the serialization API, and it allows sending serialized JavaScript objects across processes. And this mini fuzzer basically, serializes a random object, then mutates the contents of this like array buffer that it emits, and then it deserializes it back. And then we can also like do some more stuff because it's now available for the fuzzer to use. And we are fuzzing on multiple levels here, right? We are targeting the deserialization API with this like mutate function, pretty much like a binary fuzzer, but we're also like then exercising V8's handling of the result. And this is also one of the examples that the fuzzer has found. It was important to perform more operations on the result from the deserialize call. And because the object that it returned was in an inconsistent state, but the crash only manifested after we actually performed operations on them. So the program space that is now generated by these mini fuzzers is quite different from the yellow area, right? And because these like programs are somewhat unlikely to be emitted by Fuzzili on its own, Fuzzili will emit these things occasionally, but just very rarely. And now we can guide, as a researcher, we can guide Fuzzili towards these bugs and these like code shapes. And that is just, I think that is very cool because we can fuzz these very specific components. So to probably no one's surprise, building these highly specialized fuzzers can be super powerful. And these fuzzers can find bugs over a weekend on a single workstation. Because the fuzzers that we just showed you, they found most of the bugs within 24 hours on like a single workstation. So the key takeaway here is that the JavaScript search space, it's extremely large, right? And coverage guidance will only get you so far. So specific mutators can help you with specific bug types, and that is very cool. But we can also use Fuzzili basically as a framework to write new fuzzers that exercise specific code parts of V8. We can target APIs or components, and the cool thing is also prototyping them is really, really fast. It's just super nice to build them, and we can iterate very quickly. And yeah, that is everything we have for today, and thanks for listening.